All right, good afternoon, everyone. We've so far in this chapter one, diodes, we have looked at basic diode physics, semiconductor physics. We analyzed diodes using the load line, looked at the ideal diode model, analyzed using the ideal diode model, and then we looked at rectifier circuits, diode rectifier circuits. Then let me switch over to the yes, uploaded the PDF and I am recording. Yes, before you guys are never gonna let me live it down, hey. So yeah, slides are uploaded as a PDF, and I'm also recording. All right, so we looked at diode rectifier circuits with a capacitor filter, trying to approximate the the DC output voltage from a rectified AC output, right? So one other thing that we added at the end was a voltage regulator. As the name suggests, it basically regulates the output voltage, and that led us into the Zener diode. So okay, there we go. That led us into the Zener diode. We looked at the Zener diode. It's a special kind of diode that is designed to work directly in the reverse bias region without actually breaking down. So in the reverse bias region, as you all remember from the first week of class, you have the depletion region that is devoid of all carriers. When you apply a reverse bias to that depletion region, it starts widening, right? And so there is no current flow except for a very tiny amount of minority carriers that cross the junction, which is known as the saturation current. But eventually there will come a point where the junction will actually break down and you have a large influx of carriers and there's a free current flow. And so for very small increase in voltage, you have a huge amount of current flowing through the circuit. And that is indicated by this nearly vertical line in the reverse bias region. So Zener diodes are designed to operate specifically in that region, right? Without actually being damaged. Now, most diodes typically will not be damaged when you exceed the reverse voltage or the breakdown voltage. There is a reverse breakdown voltage limit. It is known as the peak inverse voltage, PIV. So circuit designers do have to keep that in mind. But again, normal diodes, if you don't exceed it for longer than a few minutes, normal diodes will be fine. And Zener diodes specifically will be completely fine. They're actually designed to operate in reverse breakdown region. So one note about it is that the characteristic for a Zener diode will always be in the third quadrant. Yes, you had a question?
Yeah, if the Zener is in the reverse bias, then if they go to 4, it's going to happen there.
Just a normal diode.
Oh.
Forward bias is just a normal diode. So in the forward bias, it just works like a normal diode. On the reverse bias, it specifically holds the voltage constant.
Yeah, I was thinking because usually the normal diode will break down if they go to the reverse breakdown section, like the Zener, like the Zener one, if you go to the forward region, it's going to break down also, or
no, there's no breakdown in the forward region.
Yeah.
It's just a normal diode.
Okay.
Yeah. Anyway, so from here, we look at the application, the whole reason why we started looking into Zener diodes, which is a Zener voltage regulator. So if we have a circuit and you connect a Zener diode at the output, the presumption is that no matter what voltage you apply, once the Zener diode breaks down, it is going to hold the output voltage constant. Now again, remember, I said we are exclusively operating in the third quadrant because both the voltage as well as the current is in the reverse region, right? So it's in the negative voltage and negative current. And so whenever we use the Zener diode, you will see it's always going to be reverse bias. Okay, so that's what you see in the circuit. Anode is right here at the bottom. Cathode is right here up top. And it is connected in reverse bias. So the Zener diode is connected in reverse bias. always in reverse bias. And so for that reason, the reference for the voltage will always have a minus sign in front of it. So even though we state this is a, let's say, for instance, 6-volt Zener, if we perform mathematical analysis to balance out our equations, that Zener voltage will have a negative sign in front of it. So minus 6 volts, right? Now, again, specification for a Zener diode will have the voltage that it is rated for and also the power handling capability. Okay, and the reason would be that if you connect the Zener diode in front of a load, the Zener holds that voltage constant, meaning a lot of the current actually flows to the Zener diode, whereas only some current actually goes to the load. Okay, so it splits the current. That's how it keeps the voltage constant. Now, as with previous analysis techniques, do not get too bogged down into the device physics. Okay, the physical analysis, like the solid state physical analysis of these devices, is a whole different course by itself. It's a graduate level course in EE, so do not get bogged down into the device physics of it. As with the diode, when we say diode is forward bias, it's on. When it's reverse bias, it's off. The Zener diode is specifically operated in the reverse bias, meaning it stays off until you exceed the VZ voltage. So VZ, again, is the Zener voltage that is part of the spec, manufacturer spec sheet. If we say Zener diode is rated for 6 volts, then the diode will stay off if the input voltage to that Zener is less than 6 volts. So Zener diode will stay off. Is off as long as V in is less than VZ. When V in exceeds VZ, what happens? You are now applying a reverse voltage that is greater than the spec. And so now the Zener diode has broken down and the junction is now open. Carriers are flooding through and you have unlimited current flow. And so now the output voltage should remain constant at VZ. So it doesn't matter how much voltage you apply, the extra current, the extra charge carriers is always going to flow through the Zener diode itself. It will hold the voltage across it constant. Okay, so once V in crosses VZ, diode is said to be on, and V out should really remain relatively stable, meaning equal to VZ. Okay, so this is this circuit right here is the simplest of circuits. We have a voltage source that has variable output. You have a Zener diode VZ, and you have a resistor R. That resistor R's job is simply to limit the current that's flowing through the circuit, right? If you don't have a resistor in a circuit, current would be infinite. So you always have a current limiting resistor. We can analyze this using load line analysis, similar to what we did for our diodes. I mean, regular diodes. So the characteristic of the Zener diode is shown right here. So this is the Zener characteristic, right? The reverse bias region, like this. Now this has a slope, but the slope is just exaggerated, just as an illustration tool for this example. Okay, typically the Zener diodes or all diodes in the reverse bias region have a nearly vertical characteristic. So this is just being exaggerated to show how the operating conditions can change, and the Zener performance can change with change in operating conditions, right? Nothing is ideal in real life. So even a Zener diode that we say stays the same for no matter what the input voltage is, there is always a slight variation, like maybe 100 millivolts, 10 millivolts. There's always some variation. So this is just an exaggeration. This is just an exaggeration. Oh, well, actually, it's written right here. So let's just use that. Okay. We analyze the circuit using the same equation because we have the same three components. We have VSS, we have R, we have VD, that is the Zener diode, and we have the current ID flowing through that Zener diode. Note the polarity and the direction of that current, right? We are still referring to the same anode to cathode, meaning anode is positive, cathode is negative. Diode voltage VD is always measured at the anode with reference to the cathode. Okay. So V out reference is plus here and minus there, which is the opposite of the diode voltage. So V out is minus VD. Does that make sense to everyone?
Can you explain that again?
So V out is basically connected across the reverse bias Zener diode. Zener diode is like any other diode. The voltage is always measured at the anode with the reference at the cathode. So VD will have a plus at the anode. V out has a plus at the top, which is where the cathode of the diode is connected. And so it's the opposite polarity of the diode voltage. So V out is minus VD. Does that make sense? Okay. Let's reduce the volume a bit. Okay. All right, so where was I? Okay, so basically this is just applying KVL around the loop, right? And we obtain VSS is R ID plus VD. Now we analyze it and we find the load line for VSS equal to 15 volts. For VSS equal to 15 volts, determine the load line and find the output voltage. So to do that, if I plug in VD is equal to 0, I get ID is equal to VSS over RD, which gives me, what is VSS? In this example, is 15 divided by 1000, gives me 15 milliamps, which is right here. Similarly, when ID is equal to 0, diode voltage VD is equal to VSS, which is equal to 15 volts. V out is equal to minus VD, so minus 15 right there. Right? Same analysis that we did for the normal diodes. Load line analysis, you simply apply KVL around the loop, you generate an equation. That equation is linear, plug in VD and ID is equal to 0 and calculate the other quantity. Once you have that, you have the load line. Once you have the load line, you find the intersection point. The intersection point is also known as the Q point or the operating point of the circuit. And we get that as minus 10. Minus 10. So V out, which is VO, is at minus 10 volts. Actually, let me write down this. Q point is at minus 10 volts. Therefore, V out is minus 10. Minus 10. Does that make sense? Right? Load line, intersect the characteristic, find the Q point, and that would give you the output voltage. Do you have a question, Jonathan? Okay. Let's take a 10-second pause. Let me know if anyone has any questions. So now the whole application at the beginning we said was voltage regulation, right? That the output voltage should not change. So now let's see what happens if our input voltage changes. So if our input voltage changes, Why does this keep doing? Okay, if I input voltage changes to, let's say, 20 volts, we now have a new load line, right? New load line. So the new load line, again, we plug in VD is equal to 0. ID is going to be minus 20 milliamps. When you plug in ID is equal to 0, you get VD is equal to minus 20 volts. And you get a new load line. So this is load line 1, load line 2, VSS is equal to 20 volts. VS is equal to 15 volts. And the new intersection point, or the new Q point, is now at minus 10.5. So now V out is minus 10.5 volts. So a 5-volt change, 5-volt change and a Zener change of 0.5 volts. It holds it nearly constant. Does that make sense? And that is only because the characteristic is exaggerated. If it was a nearly vertical line, this load line could shift as much as it wanted. Doesn't really matter. You could apply VSS, well, depending, it's an ideal Zener, can handle like hundreds of volts. That load line could shift all the way down here, hundreds of volts. But this characteristic would be nearly constant. And so the operating point would shift, but it would still, I mean, the current would shift because the let me rephrase it. The operating point would shift because the current is changing, but the voltage of that operating point would remain constant at minus 10. Does that make sense? If the Zener diode was rated as at 10 volts, the operating point would shift depending on VSS because the current would change, but the voltage of that operating point would still remain at minus 10 volts. And thus, it acts as a voltage regulator. You apply it to the output of a rectifier circuit. Even though the rectifier circuit has ripples, filtered output, the output voltage would still remain constant. All right, questions? Any questions at all?
The output remains constant because we're based on average voltage of the rectified circuit.
In the rectifier circuit?
Yeah.
Yes.
Okay.
Because so in a rectified circuit, remember we have a filtered capacitor. So our DC level, let's say it's here, right? 0 volts. And this is our, let's say, 12 volts. And we have ripple on top. So there's still some sort of AC component along with that 10 volts DC, right? So like 12, maximum peak 12 volts. Now we connect a Zener diode of 10 volts at the output of the rectifier circuit. This 10 volts DC plus the ripple of 2 volts is now applied to the Zener. As long as this input voltage stays below 10, the output also stays at 10. If it goes above 10, the Zener turns on, conducts the extra current through it, but the voltage of the output still remains 10. And so that's how it works as a voltage regulator.
So we can check our capacitors within that circuit to provide
Yes.
voltage that's constantly above it.
Yep. Yep. So anytime we want, let's say, if we want a output of like, let's say USB port, right? Our USB chargers, they need an output of 5 volts. So the filtered output that comes is much larger than 5 volts. Your battery chargers, if you're charging like a 1.5 volt battery, will always be slightly more than 1.5 volts because current will always go from high to low. So if you're trying to charge a battery 1.5 volts, Your source has to be larger than 1.5 in order for the current to actually go through there. So it's always going to be larger.
The operating range for a Zener diode that might be, in a converter for
So that depends on the spec, and that's going to be the next analysis, the Zener diode with a load. So again, Zener analysis is a lot more in-depth. We will obviously in this class, we only kind of skim the surface. We won't go too deep into it, but we look at the operating range and how we can find the operating point for a Zener diode with a load. But I am already at 1:59. There's not enough time to go through the circuit. What you're going to, we'll look at this circuit tomorrow. Well, just to give you a heads up, basically we need to actually find the Thevenin circuit to analyze. Why are you scared? You took my class.
I know. Right. I was like,
If you're scared, that means I didn't do a good job.
no. Yeah, I was like,
Okay, all right. So office hours, I have office hours from 2 to 4 today. So if anyone needs, you can stop by, or I can meet via Zoom. And then again, we'll see you tomorrow, and we'll continue on from this point on. I will have the homework for Zener sometime or tomorrow. I have to work on the solutions for the quiz. So I'll upload the recording and the quiz solution sometime later today.
okay.
So homework will be due like Sunday in time for the next. So typically I will, have the homework out like Thursday or Friday and then due on Sunday. Yes.
You know that first homework assignment you put up that was review from 201?
Uh-huh.
Is that extra credit